So let's get started. Hi everybody, I'm Alex Bertails. So I'll be speaking about banana-rdf for 40 minutes. So please interrupt me at any moment. I would prefer actually to take the questions during the talk so that I make sure everybody can follow. So what we will see today, so I want to make sure that everybody is on the same page with what RDF and linked data are. So we'll start with that. Then I will tell you, what banana-rdf is solving in this area. And along the way, I will have to explain a few things, technical things that we have to use in banana-rdf, pure Scala stuff. And I want to spend some time at the end to speak about Scala.js because actually for the past 6 months, most of the things that happen in banana-rdf are just related to Scala.js, and I have a few things to say about that. So let's start with that. So maybe a question, who here is already familiar with RDF and linked data? Okay, as expected, not a lot of people. So let's say when you think about the web, right, you have your eyes, and your browser would actually, okay, maybe I shouldn't be using that. So your browser will say, okay, I understand HTML, and we try to talk with the resource and say, okay, can I get that, please? And the server will say, okay, sure, this is the data. So if you go on my web profile, basically the browser would see that. But let's say now that you are interested in data and you say, okay, what I speak here is turtle, which is just one of the serialization for RDF, we'll see there are other ones. So I'm talking to the same resource, but this time I'm saying, oh, instead of HTML, please give me some turtle if you understand that. And that's the case for this specific resource. So I will dive a little bit into that. So RDF is, so this is RDF data expressed in Turtle. You have other ways to do that, and you have to understand the main thing is all about URIs. So unlike JSON, URI is actually a first-class citizen of RDF, and you say very simple things about these URI/entities. So in this case, the Alex hashme over there is actually a URI that denotes me, so that I can say things about me. So I can say I'm a person, I have a specific name, there is an image about me, I can expose a public key so that we can do some, we can exchange some data in a more private way. And I can actually speak about other entities as well. So here I'm saying, I know those two guys, Babelfish, Henry Story, and Tim Berners-Lee. And I can even embed information about them. But this is still part of the same document. But so that's RDF. But the cool thing is we're on the web, so there is no reason we don't want to actually go to these URLs and maybe find more information or maybe more up-to-date information. So this is actually the main there is no difference. Linked data is just RDF with HTTP. And you just want to see that. So I have a little demo. So it was hacked actually very recently. So if you want to try that, you should work in the, if you have WebGL. So I'm saying, okay, I'm starting there, and I want to go to this document. Please load the data. So that's the exact data from my server. So what you see here is actually a 3D representation of the graph of data that is behind that. So the control is not really nice with the new resolution. But you see, so that's the main, this ball is actually the main entity, me. And you see all the relations for me. So here you see there is an image, and you can see me. And I can even try to actually see what's there. So basically, you don't really know what this entity really is until you interact with it. So the same way, I can go to Tim Berners-Lee, I can unfold the data, and you can see that there is supposed to be a lot more information. Okay. Yeah, there are a few bugs, but his web profile is really big, and the graph usually is super big as well. That's very interesting. So we can play with that. Actually, we will improve this linked data explorer to make better demos in the future. This is really new. So RDF, I mean, you may not really know about it. It's actually everywhere. People use that a lot in different areas. And there are two main libraries in the Java world. So you have Jena and Sesame. And that's basically what I was using a very long time ago. That's how I started with RDF. But the way you actually write applications is still the same. So you have this really, I mean, the API is not really made for to be used on the Java side. It was mainly implemented for Spark and engines, so that people can do databases and that kind of things. But more and more, with people doing linked data, you actually want to manipulate that kind of things, and it's really horrible. I mean, there is a reason why we do Scala and we don't really do Java anymore. So what happened is that when I was at W3C a few years ago, I was working with Tim Berners-Lee on a server for private data, and so that you would exchange data using RDF, and there would be access control baked in, that kind of things. And we started. So we did that in Scala, but we were using the natively Jena. And after a while, we actually hit some limitations, and we wanted to switch to Sesame, but of course the APIs are not compatible. So we tried to extract the code, make it more common, and see how we can actually do that in Scala, in a better Scala. But we didn't want to pay the price of defining new wrappers, that kind of things. So that's basically this very similar code, but with banana-rdf. So first, you would be able to get something to read some data, and you see there is a lot more types over there. Then we can actually get the data from the web, and the main difference here is that the notion of graph, which was actually called model here, is immutable, at least by default. Doesn't mean it's persistent. I don't know if you were, I don't remember which talk this morning, but so it means basically that you can't modify the graph anymore. The API will not expose that by default. So you can read your graph from the profile, and then you have this kind of a way better API to deal with the triples in the graph. And this is all given an RDF implementation. So actually this RDF parameter here, it has to comply to a specific interface, but it doesn't say what the types are. Just we'll see what kind of constraints you have over those types. So if you were to do to implement RDF yourself from the beginning, and you had full Scala, basically the data model for RDF would look exactly like that. So a graph is just a set of triples. So it's a bag of triples, and you can iterate over them, and that's it. A triple is just subject, a predicate, and an object. That's what we see, what we saw earlier. For example, Alex knows Tim Berners-Lee, so that would be just a simple triple. And here, so always the predicate is a URI, so that's very useful because basically everything is typed. If you want to know the semantics for a specific predicate, well, you can find it. And if it's well done, you can even dereference that. You put that in your browser, or you ask for Turtle, and you get some information about it, so you can explore now what the data is all about, even if you don't know anything beforehand. So you get some data, you can actually explore what it means. And you have the notion of node. So basically that's the main component here. A node can be a URI, a B-node, or literal. So URI, you know what this is. A B-node is just like a URI, but there is no name. So there are many times you want to to build a graph of data, but you don't want to give a name to a specific node, and you don't want it to have any meaning outside of this graph. So you can't dereference that. You can just, if you found the node by following existing, a piece of the graph, then it makes sense. Otherwise, it doesn't make sense outside of the graph. And a literal, so you would find everything like integers, strings, dates. Actually, it's extensible because there is a notion of data type URI here. So you can do whatever you want, and from the world of XML, you have the language tag, EN, FR, that kind of things, and you have a lexical representation. So that actually only concerns the representation of the data. But so, for example, in Turtle, you would have a native representation for specific literals. And in an implementation like Java or Scala, you would have directly integers for a literal. You would never use the lexical representation for a literal. So this is just an API, and at the end, just the language tag is just a string. So the only problem is we can't really do that because, as we said, we didn't want to wrap anything from Jena and Sesame, so that was the main motivation. So we need to abstract over this RDF model. So we want kind of algebraic data types, but we want them to be abstracted away. And so the first thing is we need to define some kind of type hierarchy. So I would just put all those types in a main trait, and I'm just saying, okay, in order to use RDF, you need to tell me what a graph is, triple, node, URI, binode, and literal, and so on. There is actually more stuff, because it's more than just the RDF model. And we can even add some type constraints to say every time I have a URI, actually it's a node. So that's pretty easy, but you can't do anything with that because those are just types. So this is good for the compiler, but that's not enough. You need to have actual code. But actually, you probably know how to do that. Given types having operations defined over them, well, that's called a type class, and that's just what we need. So the main difference, that's a real type class. The only thing that maybe you don't really see a lot is that the parameter here is a subtype of the RDF that was actually defined here before. The reason is that we actually put all the types in one big bag, and we need to project them in order to speak about them. So we can't do that if you don't have this constraint here. So it means, given this RDF that you gave me, I can speak about the graph that is in it. I can speak about the triples that are there. So basically, we define all the operations to manipulate this the equivalent of this abstract algebraic data type. So you have everything you need. I will come back to a few things later. And at the end, what you have is not an algebraic data type, you have an abstract data type. So we define the type hierarchy, we gave names to the types, we define some relationships between them, we can even use variants if we want to. And then in the type class for the operations, the minimum that we need to be able to inject things into the types. We need to be able to extract the things from the types, and so in the case of a node, for example, we need to be able to react on the three possible choices: URI, binode, and literal. And it does that. So what does it look like now when you want to provide an implementation? Well, in the case of Jena, you just need to plug the types. So we just say, in the case of Jena, for the graph, use please this type coming from the Jena world. And that's it. We do that for everything. Then we have to define the operations. So what does it mean, for example, extracting the informations out of a triple? So given a triple, I want to have the subject, predicate, and object. Well, basically here, I have access to the Jena API, and this is where the wiring is done. And And then at the end, you need to tie everything together. So again, we had the RDF trait with the type hierarchy, and then we have an implementation just defining the types. Then we have so RDF ops is the name of the type class for all the operations for the RDF model. So we provide an implementation in Jena ops. And then we have actually to make sure that these instances are available when we need them. So it means that somehow we have to put the type class instances in the companion object for Jena. So this is happening here. And what we do is actually just to unify a little bit the names and stuff, we put everything in Jena modules so that everywhere, all the implementations, we know, it can be useful to know that the RDF ops instance is called ops. Any questions so far? So there's nothing very difficult, but it becomes interesting when you write actual code with that. So this is a very simple code, and you want to, the criteria is that I want to extract some nodes out of the graph. So it means I need to get the triples. For the triples, I want to extract the sublet predicate object. For each of them, I want to decide if I want to keep the node in the iteration, and just concatenate everything. And keeping a node here, so I need to fold over the node. So there are three cases. I will explain the construct here, because I guess you're not really used to have a fold that looks like a pattern matching, but there are good reasons for that. So I can decide, okay, is there anything interesting here in this URI? So yeah, I just want to keep it. There is a fragment, the hash thing in the URI. I don't want to keep the B node, and I keep the literal only if there is no language tag. That's just arbitrary. So there are actually a few things, from what I've showed you earlier. You should be asking, oh, but how is that possible? This node is actually an RDF node, and you're using that just like it was a plain Scala object, but there is no fold method that is exposed, so how do you do that? And the same way, this is an RDF node, but somehow, or literally better examples, you're actually able to extract some information from there. So how do you do that? And same here. So there is no triples method that is exposed on the graph in any of the APIs. So what do we do? Oh, and of course at the end, from the abstract code, you want to create something that that wires everything. So what happens is that the implicit here for the collectors will be found because of the trick of putting the RDF ops in the companion object for Jena, and that's how it works everywhere. So in a way, it's just like the cake pattern, just a lot better, but it works. It's similar in many ways. So the way it's done, so we can't really do that. Because RDF is basically abstract, so you have type erasure, so you don't have access to all that stuff. And again, this is not an algebraic data type, so you can't do that. But we want something that looks like that because that's what users are used to when they do Scala. Well, the first thing is in ops, you had this fold node. So this is very similar to the fold that you would find on option, Scala option. You can, given an option, you can say fold, and you can give there are two cases. The case where it was known, so that would be the value provided in the first parameter, or the case where it was something, and in that case you can provide a function that will use this something and do something with it. Well, here that's the same thing. You fold over the node and you have three cases, so you have three functions to provide, and the implementation will know which one it is and use that. So notice, you can see here the commas. It's because you have three parameters, so the syntax is different from the pattern matching. That being said, actually, we can use some form of pattern matching with extractors and partial functions. So we actually expose that. So it means that we, for example, in a literal, if we want to get access to the 3 components, we can write that right away, and they are bound, and then we can use them in the return function here. So how is it done? So basically, in RDF ops, by default, you provide an implementation for Jena, but what happens is that by default it will come with a DSL implementation that will use the abstract functions. So, for example, you would have a URI object that would provide an apply method and an unapply method. So if you're not familiar with that, the unapply is what's used in pattern matching. When you define a case class, an object would be created, and you would have an unapply that would actually do the actual thing in the pattern matching. So we actually expose that, and you can see that the unapply for the node is just wired to the fold node. So nothing special. And this one works for, so you can use the fold node, and this is for URI. So it means that there is nothing to extract for the B node and literal, and the unapply here is actually what's happening here, which is specialized for the URI. So you can do that. There is just one issue. I'm still not sure why, but unlike pattern matching with case classes, the U here, the type of this U would depend on the thing you are pattern matching at compile time. So it means that if you do that on a node, somehow, I don't know why, U will be bound to node instead of URI, which is not the case for case classes. I have no idea why this is the case. If you know, please tell me. And then we have some syntactic sugar. So it means that instead of writing like here, calling the fold node on the ops, we can use actually we can use it just like an object. And the way it's done is that we expose some syntax, and so that's also pretty cool. So you couldn't do it exactly like that if you were using the cake pattern, because here we want an anyval. So it means that every time you do this dot something, there will be no wrapping involved. And everything happens outside of the ops and outside of the abstractions. So, and the trick to do that is basically, so if you look at Node here, Node doesn't have the implicit ops, but you can actually push it down to the methods. So that's something you can't do otherwise. And that's why it works everywhere. So it means that when node W, the wrapper is created in this case to expose the syntax, at this time we don't have the ops in our hands, but when we call the fold, we require that it's actually available. So that's a very nice trick. So you have actually the best of both worlds. The only issue is that you have to do everything by hand. So there is actually a lot of code to expose some syntax. So I guess it could be improved. There are many ways to improve that, but still, it's not perfect. And this is available by default. So every time you import the operations, you get that for free. Try to go faster. So now we'll expose a little bit more given implementations, you can do more stuff. So you can actually use a DSL key, and with that, you can actually construct an RDF graph very easily. You can actually recognize this is an RDF graph, and it's a lot easier to share, for example, the object for that triplet here will be shared here, and that will be the subject of this pointed graph here. The notion of pointed graph is unique in the for the RDF libraries that you will find across languages. But that's super easy. It's just a graph with a pointer in the graph, and it makes it a lot easier to actually do things like finding stuff in the graph just using this XPath like DSL. So we have binders very similar to what you would find in Play for JSON. So you can go back and forth between RDF types and Scala types. Very easy. So there are a lot of defaults already provided by banana-rdf, and you can do the same for your case classes. So here you would actually define how to go back and forth with actors. So we have a query in the example code in the sample application where we go on public data sources and on DBpedia, for example, and we get the actors, and we can actually do something in the Scala world. We have support for Sparkle as well, which is the way to query RDF databases. It works as expected, but it's actually type safe again. So you pass your queries, you get actually something of the right type, not just some Sparkle query. That means that you know, for example, from a construct, it's a very specific Sparkle query, and you know that you would get back an RDF graph. Otherwise, you don't really know until you get the data. So this is more information at compile time. There are some helpers for prefixes, so you don't really want to use full URIs. So in Turtle and other serializations, you would do something like that. You would use an alias, basically. You would say everything in this ontology, this vocabulary about things. I want to be able to say fourth colon something, and I want that to be expanded to the full URI. And so we need to do that in Scala as well. The only problem, so that's an example, and here you would map the entire vocabulary for fourth, which is an ontology for friend of a friend, but that's actually huge. Like you have, I don't know, maybe 100 things. So that's actually a good use case for type providers, and Travis Brown has been playing with that, and so that's something we hope to have back into banana-rdf as soon as possible. But basically, you would actually fetch the information and populate your Scala code at compile time, and you would be able to use everything. So very recently, we actually we added mutable graphs because almost all the implementations actually rely on them. We had some very inefficient code because of that. So now we expose the mutable graphs, but they are the type hierarchy for them is different from the type hierarchy for the immutable graphs. And you can go between them. So we have a full I/O framework, which is actually very important. The main thing to remember from that, you want to be able to read and write. Okay, we have phantom types to speak about the serialization. So Turtle and RDF XML here are just two serializations. They are not useful for the code, but they are very useful if you want to tie a writer with a specific reader, for example, so you can express that. The one thing that is very important as well, because of the addition for Scala.js, I/O in JavaScript is always asynchronous, so you need futures. So we had actually to parameterize the return types for the operations. So if you're on the JVM, they happen to be single-threaded. So we use try because they can fail. But if you are in the JavaScript world, here we would say future. So so now I'll be speaking a little bit more about the Scala.js stuff that we've been doing. So because of Scala.js, the architecture of the project, it really became complex because of that. For all the projects that we want to compile for both platforms, we need to define so RDF is the core of the library. We need to define basically 3 projects, one with a shared code that is actually similar to with the 2 platforms, and then we have some code that is specific to some platforms. So for example, we have binders for dates, like Jota time, that kind of things. They would live on the JVM version of RDF core, but if we want to use the JavaScript time, then this is in the other project. And then we have an RDF test suite that can be actually consumed by all the implementations over there. So those are all the implementations that we have today. So it means that if you use banana-rdf, you can switch between them very easily. Jena and Sesame for the JVM. In JavaScript, we have n3.js and JSON-LD.js. Only n3 actually has a proper implementation of the RDF model, and we actually use that. And we have a pure Scala implementation of banana-rdf as well, which is called Plantain. And again, you have the JVM version and the JavaScript version, and they are a little bit different because you can't really use the same types. And there are other things, but they are just there. And the blue lines, there are only two here, but actually they are for all the projects over there, just for the test. So this is just a test dependency. So that's it. So that's the kind of code you can actually write today for the demo that I had a bit earlier. That was actually using that, a linked data client. So this one says, okay, so for a given RDF implementation, please give me the operations. We were talking about that earlier. Please give me an RDF reader two RDF readers. I want for Turtle and JSON-LD, which is yet another serialization. That's basically the one used by Google and that kind of all those big guys. And given a URL, I want to get a graph. So here we are using the Ajax objects from Scala.js, so this is exposed here. And we have all the nice stuff about futures, so we get the XHR object, the same one than from JavaScript. This is directly exposed to you, and then we can actually call the parsers from here. And this is in a nice flat map. So that's super cool. So basically, we had several years of work just to be able to write those 10 lines. And it worked. Well, it worked, kind of, because we were using Plantain.js for that. Plantain relied on the JavaNet URI. So in Scala.js, they had their own implementation for URI so that you can use it from Scala, but that would actually compile to JavaScript code. And when we tried that, so it was passing all the test suites, so it was perfect, we were super happy, except that we were not testing for URIs ourselves. We just assumed that the URI implementation is fine. And until this morning, so it was true that Scala.js would not support Unicode in URIs, which is unfortunate because in the RDF world there is Unicode everywhere. So they would, so we broke everything because of that. But it was amazing. In less than 10 days they added Unicode support. I haven't tested that yet, but pretty amazing. And by the way, the implementation is very simple. For the graph, it's just double index for subject, predicate, object. We are planning to support more than that in the future. So I wanted to be able to make to do the demo today. So I hacked very quickly the n3.js implementation in banana-rdf, and in n3 everything is string. So that's a JavaScript framework. They want to be fast. They don't define new object. They encode the three representation in strings. So URIs are string, literals are strings, bnodes are string as well, but they still don't expose the internals for bnodes. So here, I still need to use my own bnode implementation, which is just UUID actually. And at the end, it was super easy. I just exposed the n3.js code from JavaScript. So that's basically what I'm accessing here from Scala. And now I have access to, given a string, I can test, are you an IRI? Are you a literal? And then that would be, that's easy now to do the implementation for full node. Because this is just that, dispatching, testing the type and dispatching to the right function. So, and it worked directly. So the demo actually today uses the n3.js implementation and not Plantain.js. But now that we have the fixes for Unicode, we should be able to go back to Plantain. So, dependencies for this project. So banana-rdf is today one of the biggest user of Scala.js, I guess. So the first issues we had was really about dependencies. It's like hell. Oh, I want to use N3.js. How do I get that into my project? You need to do a web jar, but there is no web jar for N3.js. So you have to do it. The state of the art is basically using old POM XML, Maven, that kind of things. You don't really know what's happening. It's not perfect. It's you get used to it, but it was definitely an issue. But there is a problem for some of them. So, for example, JSON-LD.js, they wouldn't actually provide a browser version of the JavaScript or a Node.js version of the JavaScript. There would be only one version of it, and you can't really make. And you would actually interact with the environment to try to understand, what's the environment, so dynamically. So it doesn't really fit very well. So we had to change the code so that it could be included in the project. So this one is actually manually included today. And there are other issues, because if you want to use the real Node.js version, for example, for the test, well, you have to deal with the dependencies, the Bower dependencies and stuff, and there's nothing helping you. Other things, the dependencies, those dependencies, they are not included by default, so that's a common mistake. You need actually to bind your code to JS depths. Just need to know that, because actually they didn't plan that people would be using WebJS, Scala.js that way. So just is there, but you need to know how it works. And yeah, again, a dependency hell. It really feels like, the transition from Scala 2.7 to 2.8. I don't know if you were around at that time, but it was like hell, trying to get everybody to update and getting the right versions, deploying everything. That's really the state of Scala.js today. It will get better, of course, but still an issue. Tooling, there are some good things and bad things, I think. SBD Scala.js, so we have actually, one of the guys working on banana-rdf has made his own version of SBD Scala.js, so the SBD plugin for Scala.js, because they apparently, I don't know the specifics, but doesn't support all the IDEs and that kind of things. So until this morning, JavaNet URI was a real issue. Testing today, so we are using zcheck, or zcheck, I don't know, which is basically a spec-lite from Scala-Z, so it was extracted, and because of that, we had to patch Scala check so that it would actually be able to compile down to Scala.js. So it was a lot of changes, and it happened just to make zcheck possible. But there is utest, which is a new library that, so the sample project actually uses utest, which is awesome. You should check that out. Even if you do only JVM testing, I think that's the best library out there now. Dealing with environments, so today you need to test with Node.js or Rhino or something like that, but this is different from testing for the browser. And I wish we had something like Jasmine or something like that would be super nice, so that we could actually execute the test in the browser, because that's, at least in our case, that's the target. Travis CI, we had so many issues actually to make Travis to accept all the tests. Still open issues, I guess. It might be on our side, we don't know. It's probably on my side, I guess. But we can't activate Node.js. Node.js is a lot faster, but apparently having Node.js for all the JavaScript projects just doesn't work, and we use all the memory. So what's next for banana-rdf? So we want to get to 1.0. It's been 4 years already, but we want to get to 1.0 after we fix a few issues in the IO abstractions. That's because of Scala.js, actually. We want some proper documentation. I will go, I'm not sure I have time to really explain everything here. I want to make sure people have time for questions, but yeah, we have a lot of ideas to improve banana-rdf. So some reading, the project itself is there. There is a sample project that actually makes use of most of the features. The live demo, WebGL demo, which was actually full Scala.js, by the way, is there, and we will be improving that. For the encoding of the type class thing, I wrote an article a few months ago. You can go there. And so the work that, everything that works today, it was actually, most of the things that happened were not made by me, and all those persons were directly involved in the result of today. That's what I have, thanks. So if you have questions. Is there any question? And I was told if you have questions, you need to come to the mic. Yes.
Hi, Alexandre.
Hi.
Thanks for the great talk. So I was poking around open source to find some interesting RDF bindings, and I seen a few, and one of them was rdf. It's a legacy project which has fairly evolved bindings and DSLs, and there are a few updates. I wonder how banana-rdf relates to this and maybe some other bindings, and is this now the primary Scala binding we should use for RDF?
Yeah, so I haven't checked Scala.rdf, that's the name, right? In a very, very long time. At the time, it was mainly wrapping things around. The DSL was a little bit weird, and basically, for a very long time, the project was dead. So I don't know if it's not undead now. I'm not sure. But we've had actually a lot of people contacting us because they were using banana-rdf. I've never heard of people using Scala.df, but it's possible. I guess we were lucky. I studied that when I was at W3C, where RDF was defined, so it was maybe a little easier for us to sell the library, so it helped. Right, any other question? Okay, thank you all.